Hi, myself Dr.G.Tharanitharan. This is the seventh video series of additive manufacturing and its types. In this session, we're going to see about laser metal deposition method. Is an additive manufacturing process in which feedstock material is melted with laser and then deposited into the substrate. The wide variety of pure metals and alloys can be used as a feedstock as well as composite metals such as metal metric composite. The laser source with the wide varieties of intensities and wavelength and optical configuration can be used. While LMD is typically a melt based process, this is not a requirement as discussed below. The metal based process typically have a strength advantage due to achieving the full metallurgical fusions. Now I am going to explain about the laser source and its importance. As with lasers, selective laser centering, the laser pulse does not have especially high as long as laser energy is sufficiently concentrated. The achievable rate of the material addition depends on both the amount of laser powder applied and heat of the fusion of the feedstock and substrate material. As a different material absorbs the different wavelength of light, it's important of the wavelength of the laser source is approximately matched to the material absorption spectrum to ensure the amount of energy absorbed by the material is maximized. For example, using LMD to deposit the steel is efficiently performed using IR laser resources, while for the copper-based alloy green lasers have the better absorption. Next, I'm going to explain the different types of LMD process with both feedbacks. First one is a pre-placed powder. This simplest LMD technique involves the pre-placed powders. The powder feedback is powdered into the surface of the substrate and focused on layer is scanned or restricted over its causing the feedbacks to melt and fuse with the substrate. Typically, the inner shielding gas is used to reduce the oxidation around the melt zone. The process is similar to the selective laser sintering, which is systematically layer by layer process building of an object by using a layer selective fusion with a bed of powders. Conventionally, in conventional powder bed LMD, the powder or nozzles are used along with focused laser resources. The laser is focused on the substrate to form a metal pool. Simultaneously, the powder is sprayed of the nozzle as a powder jet flame, directing material into the melt pool where it melts. As a laser source move away, the melt pool follows with the materials at the previous location of solidifying. The process is typically achieved using a laser cladding heads which integrate the powder nozzles and laser optics into the one assembly with both focused at single target locations. The size and area of the metal pool and powder plum may vary widely and may take on the spot or light configuration depending on the target application. As the powder placed LMD shielding gas is typically used to minimize the oxidation, the carries gas is used to deliver the powder is also typically the shielding gas. The LMD process can be used in many ways such as scanning over the white surface to build less than 1 micrometer coating of the object of rastering the one particular area of an additive manufacturing process to build the object in 3D layer by layer. This is some high conventional options for laser metal deposition. Next, the speed wise we're going to discuss about this method. The high speed LMD method differs from conventional LMD in focal point of the laser and in the speed of cladding process. For high speed LMD, the focus point is located above the substrate. As the powder is sprayed through the focus point, most of the laser's energy is absorbed by the powder while it's melted in the flight. This results in molten powder feedback impacting the substrate where heat is transferred from powder into the substrate. Typical result in the lowest portion of the thermal energy being transferred into the substrate, and as in the result, the high speed LMD produces a thinner well bead deposits with lower dilutions and thinner heat affected zone compared to conventional LMD. So the speed of the depositions is typically at least of 10 times higher than the speed of the conventional LMD, and rate of material solidification is also possible. The typical effect of this difference compared to conventional LMD is a deposit with a smoother surface finish, finer grain microstructure, improved corrosion resistance, and high hardness. Both 3D coating and 3D additive manufacturing also being possible with the case of high speed LMD. Thank you.